All right, today we are jumping right to the edge of known physics. We're going to talk about a leap in computing that is poised to completely reshape our world. We're talking about the huge shift from classical to quantum.
Okay, I want you to just imagine a problem so ridiculously complex, so massive that our most powerful supercomputers, and I mean machines that do quadrillions of calculations a second, would need 10,000 years to solve it. This isn't science fiction, by the way. These are the real challenges we're up against in fields like medicine and material science.
Now, what if I told you that back in 2019, a totally new kind of machine solved that exact same problem in just 200 seconds? That's what Google's Sycamore quantum processor did. In less time than it takes to make a cup of coffee, it did something that would take our current tech more than a lifetime.
And that incredible jump in power, that really gets to the core of what quantum computing is all about. See, it's not just about being faster. It's a fundamentally different way of looking at the world, of processing information. It's a way that, well, it actually mirrors the mind-bending complexity of the universe itself.
So to really understand where we're going with this, we first have to get a handle on the limits of where we are right now. We've basically hit what you could call a computational wall.
Look, don't get me wrong, our supercomputers are absolute marvels. They're giants. They tackle huge jobs like forecasting weather with thousands of processors all working together. But here's the thing, at their core, they're still built on classical physics. They're still speaking a simple language of zeros and ones. And when you ask them to describe something truly complex, like nature at the molecular level, the problem's complexity just explodes. It grows exponentially. And even our very best machines, they just grind to a halt.
So, if classical computing is stuck at this wall, how do we get past it? This is where the quantum difference comes into play. It doesn't try to climb the wall, it just builds a door and walks right through it. You know, the physicist Richard Feynman absolutely nailed it with this quote. He basically realized that trying to simulate the quantum world with a classical computer was like, I don't know, trying to build a skyscraper with Legos. It just doesn't work. To solve problems that play by the rules of quantum mechanics, you need a machine that plays by those same rules.
And it all comes down to the most fundamental building block. A classical computer uses a bit. It's just a switch, right? It's either on or off, a 0 or a 1. Simple. But a quantum computer uses a qubit. And this is where things get really weird. So stick with me. Because of quantum mechanics, a qubit can be a 0, a 1, or, and this is the key, both at the exact same time. That one single difference is why its power scales exponentially.
This strange ability to exist in multiple states at once, it actually has a name. It's called superposition. You can think of it as the qubit superpower. It's what allows a quantum computer to explore this massive landscape of possibilities all at once, instead of having to plod along and check each path one by one like a classical computer has to.
So because these machines are operating on principles that are just so bizarre, you have to completely forget everything you think a computer looks like. We are not talking about a sleek box with some blinking lights here. Not even close. A quantum computer often looks more like a beautiful, incredibly intricate chandelier. And this whole design, it's all there for one reason, to protect the qubits. They are so fragile. They have to be shielded from any outside noise, electrical, magnetic, even a tiny change in heat. I mean, they have to be cooled down to temperatures colder than deep space, right near absolute zero, just to keep those qubits stable enough to do their job.
Okay, so we've got this unbelievably powerful but also incredibly delicate new kind of machine. Why on earth would we go to all this trouble? Well, because this opens up a whole new world of problems that we can finally tackle.
Now let's be super clear here. You are not going to be checking your email on one of these things. Their power is being saved for humanity's biggest, gnarliest challenges. We're talking about designing life-saving drugs in days instead of decades, because you can perfectly simulate how they'll react with proteins in the human body. Imagine discovering brand new materials to build hyper-efficient batteries, or creating financial models that can predict market crashes with stunning accuracy. I mean, the potential is just staggering. But, and you knew there was a but coming, this immense power is a double-edged sword, because with the ability to solve these massive problems comes the ability to break the very systems that protect our entire digital world.
You see, the complex math that keeps everything secure, from your bank account to your private messages, it all relies on problems that are just too hard for classical computers to solve in any reasonable time frame. But for a powerful quantum computer, breaking that encryption, well, it's just another puzzle to solve.
And this has led to a really urgent threat that security experts call steal now, crack later. Here's how it works. Right now, as we speak, bad actors are just vacuuming up massive amounts of encrypted data. It's useless to them today, but they're not trying to read it today. They're stockpiling it, just waiting for the day they can get their hands on a quantum computer powerful enough to unlock all of it at once.
So look, quantum computers are not going to replace your laptop. They're going to work alongside our classical machines, unlocking just incredible progress. But their arrival starts a clock. A race is on, not just to build these amazing machines, but to build a whole new generation of security that can defend against them. So the real question isn't if quantum computers are coming, it's will we be ready when they get here?